All right, so a vector is a quantity that has both a magnitude and a direction. Have you guys heard that term vector before? Yes, where have you heard it before?
Physics, or no, a lot.
Huh? Where?
Physics?
Yeah.
Yeah.
What's a vector in physics? Like, where would you?
Yeah, like it's like how, like where something going, I guess.
Right. Right. So basically, anytime something has a magnitude and a direction, it's a vector. So an example of a vector quantity would be velocity and force. These are vector quantities. Whereas, let's say, speed is not a vector quantity, okay? So if a quantity only has a magnitude and no direction, it is called a scalar. So the two different quantities are either a vector or a scalar. So for example, if you say, so the velocity of an object would be 6 meters per second east. So you see how that has a quantity, or a magnitude, 6 meters per second, and a direction east. Because this quantity has a magnitude and a direction, it's a vector quantity. So velocity is a vector quantity. Speed, if you just say, the speed is 6 meters per second with no direction, that's a scalar quantity. Okay? All right. So take a look here. Let's see if these are vectors or scalars. A ball is thrown northwest at 60 meters per second. Vector. How about the next one? A tennis ball is served at 110 miles an hour. Scalar. How about a sprinter running 100 meters north? Vector. So the thing is, it doesn't only have to be velocity. Velocity and force are only two examples of vectors. Many, many other things can also be vectors. Anytime a quantity has a magnitude and a direction, it's a vector. So for example, this one, okay, 100 meters is distance. 100 meters north is displacement. That's a vector quantity. Okay? All right. So because of this idea of direction, vectors are usually represented as an arrow diagram, or another term for it is a directed line segment. So take a look here. This is the vector. Do you see how it looks like a ray in geometry, where it has an endpoint and it's got an arrow on the other side, right? So that's the direction in which it's pointing. And just like in the case of a ray in geometry, the order of it matters. You can't switch AB versus BA, right? Same thing with this one. The direction really matters, okay? And the endpoint and the other point really matters. So let's look at some of the parts of this vector. The endpoint, as we're used to calling it, is called the initial point, or the tail. B here, where it points, is the terminal point, or the head, or the tip. Okay? I like initial and terminal point, or tip and tail, personally. The difference between a vector and a ray is a ray stretches infinitely in one direction, right? The direction of the arrow. Not so for the vector. It points from A to B, and it ends from, at B as well. But the direction that it's pointing is there, okay? So it's a finite length. Okay, notation. How do we, what do we call vectors? How do we label them? Well, you can use two capital letters as the initial and the terminal point, and it'll be vector AB, like this one, always starting at the initial point A and B. So never BA, AB, right? Okay, and the symbol above it, so if you were writing it, AB, it's a one-sided arrow, like this, okay? Yeah. Just a one-sided arrow, okay. Or you can give the entire vector a symbol, like lowercase a, that's lowercase. So you can call this vector A, okay? Or in books, it's also written in bold, but obviously in handwriting, we can't bolden the letter, so it would be this. So it's half an arrow, not a full arrow on top. If it was a full arrow, it would be a ray. This is a vector, different notation, okay? A full arrow would be wrong. Okay. Okay, when a vector is in standard position, its initial point is at the origin. So just like this one. Do you remember when we used to put angles in standard position, right? And the initial side would be at the x-axis. Remember that? So same idea. Now, we said a vector has a direction and a magnitude. So let's talk about direction. The direction of the vector is just an angle. That's how you give direction between the vector and a horizontal line. So for example, take a look at this vector. It's in standard position because its initial point is at the origin. This is the horizontal line from which it sort of originated. You go up 35 degrees from the x-axis to the vector. That's the direction of the vector, 35 degrees. So if you say the vector has a direction of 35 degrees, there is really no other way to draw it, because you start from the horizontal, go up 35 degrees, there is no way to draw it other way, okay? The magnitude of the vector is the physical length of the line segment, and the symbol for that is with the bars. So if you were to write it, this would be the magnitude of the vector. It's the size of the vector. Okay? So if you were to take a ruler and measure this, okay, that would be the magnitude of the vector. Now, because vectors can represent, all sorts of things, a force, a velocity, whatever. Suppose a vector represented the velocity of an airplane, like 760 miles an hour. You're not going to draw an arrow 760 units long. That's just crazy. So we scale it down, okay? So for example, in this vector, 1 centimeter represents 5 feet per second. So suppose I took my ruler and I measured this, and suppose I measured this to be 2.6 centimeters. Because when you measure it, I think it is 2.6 centimeters. Well, what's the magnitude then? If every centimeter is 5 feet, then the magnitude is 5 times 2.6, 13 feet per second. Does that make sense? Okay. Questions? Yeah. No. I'm just giving you an idea. You're not going to need a protractor. Okay. So let's talk about how to find direction of a vector. Look at this vector A, okay? To find the direction, here's what you do. Draw a horizontal line at the tail of A. So if this blue is the vector A, the tail is right here, the end point, right? From the tail, you draw a horizontal line like this, okay? Then you measure the angle from the horizontal line to A in the counterclockwise direction. So just measure that, and it would be, let's say, 123 degrees, whatever, okay? So suppose the angle was pointing this way. Suppose this is vector B. How would you measure the angle there? Same thing. Find the tail, draw a horizontal line, and then we measure the angle from here, from this, right, in the counterclockwise direction to B, So it would be, let's say, 217 degrees. I don't know. Okay? Yeah. Yeah. It's like the positive x-axis. Just like with other angles in chapter 4. Yeah. Okay? Yeah, I know. See? That's how good I am at this. Okay. All right. Hello. Come in. Okay. So, all right. So let's talk about, again, like parallel and equivalent and so on. Okay. So these are a couple of vectors, right? A few vectors. So suppose you had like a handful of vectors and you threw them up in the air and they landed on the paper the way they landed on the paper, right? So you've got vectors A through F. Okay. We say vectors are parallel if they have the same or opposite direction, but not necessarily the same magnitude, okay? So, take a look at vector A here, okay? This vector A. Which one of these would you say it's parallel to? B. Okay, what else? C and E and F, right? Good. Okay, so now equivalent vectors are identical vectors. They have the same magnitude and the same direction. So let's take A again. Why not? What would you say is an equivalent vector to A? Which one? So, okay, so we want the same direction and the same magnitude. So C, right? And so we say vector A is equal to vector C. Okay? And so with the real numbers, right, we know what equality means. With vectors, this is what equality means. Okay. Opposite vectors have the same magnitude but opposite directions. So for example, E and A. Do you see E and A here? This one and this one. Same magnitude, opposite direction, and the way you write it is you say vector E is the same as the negative of vector A. So what do you notice here? This negative, right? What does it signify then? That it's opposite, so it's direction, right? So just like if somebody's velocity was like positive 70 miles an hour or negative 70 miles an hour, that negative, the sign, would tell you the direction. Okay? Awesome. So, so that means direction. All right, so let's talk about what to do with vectors. Okay, so we're just getting the law of the layout of the land here, right? Remember with matrices, before we learned how to work with them, we were like, okay, what can you do with them? How do you add them? How do you multiply them? And you saw that adding and multiplying vectors were like two completely different situations, yeah? Okay, so matrices. Let's talk about what it means to add matrices. I'm sorry, vectors. So we know what happens when we add two real numbers. We're used to that operation, yeah? 5 plus 3, you get 8, right? You get another real number, and so on. Okay, when you add two vectors, the sum, right, the result, is called a resultant vector. Okay? All right, so here's how vectors add. To find the resultant vector, well, there are two methods. One is the triangle method, one is the parallelogram method. This is the one we're doing today. So you have a vector A and a vector B. You're going to find A plus B. Okay? All right, so here we go. Step 1, translate or shift B so that its tail touches the tip of A. All right, so you see the two vectors here? You physically take this one and just move it over so that the tail touches the tip of this. So now imagine this was somebody's route, okay? And then this was a continuation of their route. It's just broken up and you're like sort of reconstructing it, right? So they walked along the red arrow and now they're gonna continue along the blue arrow. So that's what you wanna do. First part and then the continuation, okay? So that's the first thing. Just move them and put the tail to the tip. Next, you're gonna draw a third vector from the tail of A to the tip of B. So where's the tail of A? Here. Where's the tip of B? Here. You draw your third vector from one to the other, okay? That is your resultant, and it could be labeled A plus B. Okay, you could also call it vector R. Now, remember we're talking about route. So suppose this person started at this place, start. They went along A a little bit, then they went along B a little bit, and this is where they ended, right? Potentially, you can also draw that route along the green arrow. They started here, they stopped there. So the arrow on the green has to signify where they started and where they ended, right? So that's how you would draw A plus B. Now, the magnitude is the physical size of the vector, right? And then the direction we just talked about is the angle from 0. Okay? Now, we're just going to practice with these. I'm not going to have you take out a protractor and measure them, but I want you to be able to draw what R plus W would look like. Okay? So, take a look at V here. We want to draw V plus W. Okay, so what I'm going to do is I'm going to take this, reproduce it here. I'm okay with you just sort of, you know, you don't have to be super precise with this. Again, I just want to get you used to the idea of how to draw the resultant. So this is vector V, yes? We're going to take W and translate it so that it's at the tip of this one. So W here. Okay? You've done nothing so far. You have not added two vectors. You've just redrawn two arrows, right? To draw the resultant vector, you have to go from the very beginning to the very end. Okay? So from here to here. And which way would the arrow go? Up or down? Up. Okay? So that new vector is V plus W. Okay? Yeah. Okay, no, that's a good question. And we're actually going to look at that like at the end of this lesson because we're actually going to do it with a couple of examples. Yeah, so they're not going to add just like numbers do. Okay? All right. So take a look at this one. I've got vector A here. Okay? So here we go. Tip and tail. And negative A, right? Where would negative A start? Where would you start drawing it? At the arrow of this one, right? And I'm going to draw it this way. Right? That's negative A. Yes? Did we do that correctly? So now, what about the resultant? 0? What do you guys think? 0? 0 it is. Okay? So remember what we said before is that, you know, they have the same direction, but, they have opposite direction, but the same magnitude, so they would cancel each other out. Okay, let's do this next one. 25 newtons north, and then 35 newtons south. So if I were to draw an arrow that's 25 newtons north, okay? And then starting from the arrow there, I want to draw one that goes 35 newtons south. Where does it go? Down. Okay, and I want to make that one a little bit longer, right? Okay, so what's the resultant? It goes from the beginning of my story to the very end. Okay, so how much would be the balance there? 10. Right? Okay, so it would be 10 newtons south. Okay, all right. Do you remember we dealt with scalars with matrices? You remember we had to multiply a scalar, right? Okay. All right, so same situation here. We talked about scalars and vectors earlier today. If you have a vector, A, multiplying it by a scalar would change its size. So it would multiply it by, by 3 in this case, make it 3 times bigger, or by a half, and so on. All right? So here's 1A and 3A. It would make it 3 times as large. Okay? All right. So take a look at what we have here. I have vectors x and y. What I want to draw is 3 times x minus 3/4 y. Okay? So if I were to draw 3x, what would that do to that x vector? Make it 3 times bigger, right? It wouldn't change the direction, right? Okay, so the other one is negative 3/4 y. So first of all, how much is 3/4 y? What would that what would happen to that vector? It's smaller, right? But then, so, 3/4 the size, right? But then if you have minus 3/4 y, that also changes the direction, right? So it would be a smaller vector than that here. Okay? And okay, so the sum here of these two, right, the sum, that's the resultant vector, right? So it would go from the beginning here all the way there. So look, the blue is the vector 3x. This is just negative 3/4 y. But that sum, that quantity, 3x minus 3/4 y, that's that green over there. Oops. Okay? Yep. Okay, questions? We might even have some time for those jokes later. We had to write jokes on the test last time. We had a thoroughly fun time in the family reading them last night. I was just telling them. Yep, it was like Super Bowl, then the jokes. Okay, all right. Okay, so let's talk about vector components. Okay. How are you guys doing? You're awfully quiet. I know. Okay. All right. So vectors which add to create another vector are vector components, right? So take a look here. These two added to create the green, right? And we did another example up above. What if I gave you the green and I said find two vectors that would add to create that, right? Can we go backwards? I mean, why not, right? What do you think? So suppose I gave you a vector, right? Let me put up a vector here, like this, okay? And can we create two that would add to this? I mean, we can, right? Like that, we could have a vector like that and another vector like that, right? If this was my vector v, right? Are there any other options? How many other options are there? Infinitely many, right? Like here and here, right? So I can draw like a whole bunch of different ones. However, there is one situation that's like the most convenient for us to work with. Those are called the rectangular components. Okay? So I can take that vector and I can decompose it into its rectangular components, meaning the components would be horizontal and vertical, right? So here's one, and here's another one. Okay, let's align them. Okay, this would be a 90-degree angle. Okay, and now look, this is vector v. We have to have the arrows aligned properly, right? So if, again, we were trying to get from here to here, I can have two possible routes. One is along the vector that way. Another is along the purple components this way and that way, right? So your arrows have to like feed into each other, yeah.
You also go up.
You can also go up and go over. Way to go, yes. Let's see what would happen if you did that. Up and over. And so compare the two vertical ones. Are they the same? Yes, and what about the horizontal ones? They're also the same, right? Okay. That's exciting. Okay, and we call this the x component and the y component, right? Okay, so draw the ones for the other one. Let's draw the ones for the other one. Which direction would we go? Down and right, or up and right, or maybe left and down. What do you guys think? So we're going to start from here. Where? Up. And left. Okay. And we can call that the x and the y component like that. Fantastic. Okay? All right, let's make that a 90-degree angle. Okay. So, all right. So while digging in his garden. Okay, so I know this, you know, you're like, who digs in their garden? Okay, so like all three of my boys and my husband are constantly doing this. So I read this problem and I'm like, yeah. Will's digging in his garden, right? So it's not really that far removed from me. So there you go. So Will pushes a shovel into the ground with a force of 630 newtons at an angle 70 degrees with the ground. Okay? So first what we have to do is draw the diagram that shows the resolution of this into its rectangular components. All right, so let's draw this. First, let's draw the shovel. Okay, let's draw the shovel. Here is the shovel. Okay. 70 degrees with the horizontal. Okay. So now what we want to do is we want to draw the rectangular components. So in what direction? If we start here, up and left, or down and let's go down and where? Right. Okay. So this is the x component and the y component. Okay. And where is the 70 degrees? Is it up here or down here?
No.
Down, right at 70 degrees with the horizontal. Okay. 90-degree angle there. Hey, so you remember trig from chapter 4? Yeah?
Yes.
Guess what? It's back. It's back. Have you guys read The Shining? Have you? There's a line in there that goes, I'm back. You haven't read The Shining? All right, maybe we'll read it as a class. No, we will not. All right, so let's do this. We're gonna need our calculators for this. I know. Remember those calculators?
Yeah, I'm really excited.
It's exciting.
Yeah,
I know. Okay, so we're going to find the magnitudes of the horizontal and the vertical components of the force. Okay, so where's the horizontal component? There.
It's is it sine?
Okay,
Yes.
well, look at this. This is supposed to represent the force. Okay, we're going to call it vector F. And how much force does he exert? 630 newtons. So now, look at the x component there. Oh, adjacent over opposite. That sounds like cosine. So katoa, cosine of 70 is x over 630.
I thought you were lying when I asked last chapter if we were ever going to deal with this again.
Why would I lie to you? What do you think? I'm a liar?
I don't know.
You calling me a liar now?
And now it's actually back.
Now it's back. So
Hey,
this is the component. I mean, this is the magnitude. So x is, what's x? 630 cosine 70. Okay, go ahead and put it in your calculator. What mode should your calculator be in?
degrees.
70 degrees, yes.
Why is an absolute value?
It's the magnitude. 250, it's the magnitude, the size. So magnitude is always an absolute in the bars. Just like determinant was in bars. Yeah. Okay. So now, let's do the sine of 70. Is y, the magnitude, the size of y, over 630. So y is 630 sine 70. How much is that? Ooh. Okay, so, okay, let's take a look at some notation. If I were to say, okay, the x component, okay, is equal to 215.5 newtons, what is that, east? Now this has magnitude and direction. I have given the full-fledged vector, no bars, okay? If I do this, then I strip away the direction and I say 215.5 newtons. This is now a specific sized vector and I'm not specifying where it points. Okay? Yeah.
So that
It's like a revolving door in here today. Okay. Yep.
So would it be Like, would that be the difference between like using negative versus not?
Yep. Okay, so take a look at x and y. If you were to add 250 and 592, would that give you 630?
Oh,
Probably.
no.
No.
No, because if you add the 200 to this, you're already at
I
700.
just realized you done
Right, because, but,
Close.
y plus x, vector y plus vector x do add to this vector. So do you see how vector addition is not just adding the magnitudes of the components? So it's not straight addition like you think it is. Okay?
If it forms a right triangle, could you use the Pythagorean?
You can use the Pythagorean theorem.
Separate.
This you will find is so much more useful though, because
it looks easier.
it's so much easier. Okay, so let's do another one.
Yay.
A player kicks a soccer ball so that it leaves the ground, leaves with an S, the ground, with a velocity of 44 feet per second at an angle of 33 degrees with the ground. Okay? So there we go. That's, I don't know who that is, whether it's Messi or Ronaldo or, I don't know. Huh? Could be. There is no one around him, and he does sort of ignore his team, so maybe it could be Ronaldo. Anyways, what was that? Where did that come from? There's no hidden agenda against Ronaldo here. Okay. Okay. So draw a diagram that shows the resolution of this force into its rectangular components. Here we go. That vector is 44 feet per second. You know, we'll call it vector v because it's velocity. Okay, horizontal and vertical components. Here we go. Horizontal component, vertical component. Let's do this. 90 degrees. Okay. Okay, find the magnitude of the horizontal and the vertical components. So where's the magnitude here? What are we going to do? Do we have an angle?
No.
33.
33 degrees. Okay, so
We do cosine
33,
33 equals x over 46.
right? So x is 44 cosine 33. And how much is that? 36.9 feet per second. Okay. And then the sine of 33 is y over 44. Yes, eventually. I mean, you know. Oh, I meant to write it like this. So y equals 44 sine 33. How much is that? Yep. Maybe let's do 24.0 feet per second. Okay, so look at this. So this person kicked the ball at an angle of 33 degrees. And do you see how the horizontal component has a velocity of 37 almost, whereas the vertical component has a velocity of 24, right? So because it's got a larger horizontal velocity, this is going to go farther horizontally than it will go up, right? Like sometimes you see, you know, like when there's like a goal attempt, right? The goalie on the other side will, right? Like we'll kick the ball all the way to the other side and they really kick it really high, right? And so it goes like way up high and then, right? So you see the different angle at which the ball is kicked will make a difference. So that's what these do. Okay, so at every single time, at every single point here, some of that velocity is going in the upward direction and some in the horizontal direction. And so, and you know, but together they all add up to that vector. Okay, and so, you know, together they play together in, you know, coordinating sort of where all this is going to go. Okay, now, yes.
Two questions.
Yep.
So one, would the answer for this would be 36.9 and 24,
Right, the horizontal and the vertical component, yes, it would be this,
Okay.
this.
And then second, on the last question, where it said the shovel, how do you know to draw it down?
The what?
The
Oh, the
shovel.
shovel? Well, because it's the direct, because like he's, like he's digging into the ground in the downward direction. So his force is going into the downward direction. It's not like he's like punching up in the sky, right?
Yeah.
That's why. So it's the direction of the force, right? It's literally directed through the arms into the ground, okay? All right, so let's recap. Do we see any patterns here? I see some patterns, but do you see some patterns? In this case, when we wanted to find the x component, what did we do? The main vector was 630 cosine 70. Here, it's the main vector cosine 33. So that must mean that the x component is always the main vector times cosine of theta. And what about the vertical? Look, it's 630 times the sine of the angle. What about here? Oh, it's the magnitude of the vector times the sine of the angle. So that must really be a thing. And if it's in a box, then it is a thing, right? Right? So you can potentially, when you're finding magnitude, you can skip that first step and just go to the second step. Okay? That's what we're going to do eventually. That's what I need you to do eventually. Okay, how does that sound?
That sounds good.